In this presentation, I will resume explaining the moving boundary work topic but focuses on polytropic process. During actual expansion and compression processes of gases, pressure and volume are often related by a relationship of PV to the power n equals C, where n and C are constants. A process of this kind is called a polytropic process. The process is depicted in the given figure. A general expression for the work done during a polytropic process can be expressed in the pressure terminology. Before that, let me introduce the pressure for a polytropic process as shown here. Substituting the pressure relation for the polytropic process into the boundary work equation yields a given expression. Since C equals P1 V1 to the power n equals P2 V2 to the power n. For an ideal gas, the boundary work equation can also be expressed as in the given form, since PV equal mRT. However, for the particular case of n equals 1, the boundary work becomes the given equation, where for an ideal gas, this result is equivalent to the isothermal process. Now, let us learn this knowledge further by understanding the following example. In this example, a gas in a piston cylinder device equipped with a linear spring expands due to heating. The final gas pressure, the total work done, and the fraction of the work done to compress the spring are to be determined. Before we solve the problem, we must first specify the assumptions for simplification as follows. First, the expansion process is quasi-equilibrium, and second, the spring is linear in the range of interest. Three systematic steps can be used to determine the final gas pressure, the total work done, and the fraction of the work done to compress the spring as described here. First, we must determine all the related states of the gas using the given information. Second, sketch the process curve on a PV diagram. And third, establish the equations to be used to determine all the above. For step 1, we begin by determining the gas properties at state 1 using the available information. The gas initial volume and pressure have been given as 0.05 cubic meter and 200 kilopascals, respectively. Therefore, these properties represent state 1. For state 2, We can quickly calculate V2 since the final volume inside the cylinder doubles due to heat transfer to the gas causes the piston to rise and compress the spring. This can be demonstrated here. Therefore, V2 equals 0.1 cubic meter. P2 can be determined by adding the additional pressure with P1. The additional pressure is due to force applied by the linear spring at the final state. This can be expressed as in the given form. The additional pressure applied to the gas at this state is as shown here. F is the force applied to the gas by the linear spring and denoted as presented. Delta X is the displacement of the piston due to the force applied by the linear spring. It is defined as illustrated here. Therefore, the force applied by the linear spring becomes 30 kilonewtons. Therefore, P2 can be determined as demonstrated here. After the related properties for states 1 and 2 have been determined, we can easily sketch the process curve of the system on a PV diagram as demonstrated here. Now, we go back to the problem described in example 4.4. The gas pressure at the final state is simply 320 kilopascals. Without the spring, the gas pressure would remain constant at 200 kilopascals while the piston is rising. But under the effect of the spring, the pressure rises linearly from 200 kilopascals to 320 kilopascals. To find the work done quickly, we can plot the process on a PV diagram and find the area under the process curve, as demonstrated here. Note that the work is done by the system. The work represented by the rectangular area, that is region 1, is done against the piston and the atmosphere. The work represented by the triangular area, that is region 2, is done against the spring. Thus, it is 3 kilojoules.